Hi, in this video, I'm going to talk about more bit operations, specifically AND, OR, and NOT. So the first operation is called a bitwise AND, and I'm showing you how to do it for 1 bit first. So a bitwise AND operation, it takes 2 operands, A and B. And as we know, if there are 2 bits, then there are 4 possible combinations, right? 0, 1, 0, sorry, 0, 0, 0, 1, 1, 0, and 1, 1. And the result of 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0. And the only time that it results in 1 is 1 and 1. Right? So this is very similar to the logical operation that we are familiar with before. Now, the reason it's called a bitwise AND is that not only it works on operands with just 1 bit, but it works on operands with multiple bits. So, for example, so if the A and B, if the operand, if A is 0, 1, then 0, 1, and if B is 0, 1, 1, 0, then and the bitwise AND operation, what it does is that, well, first we just line up all the bits by the least significant bits, and then we just take a pair of each bit and do the AND operation on them. Right. So, for example, the least significant bits are 1 and 0, so that gives us a 0, and then 0 and 1 also gives us a 0. 1 and 1 will give us a 1, and 0 and 0 will give us 0. So the result is then 0, 1, 0, 0. Now, as I said just now, that the bitwise AND operation is actually very similar to the logical AND operation that we use in conditionals. Right? In that case, A and A, the only time that it evaluates to true is if both A and B are true. However, they are different in that the logical AND, it may be short-circuited, and let me explain what that means. So I actually wrote a little kind of a trivial function here called full, and when it's called, it would print out that, hey, I'm in full, and then it just returns a number, in this case a 1. Okay, now when we evaluate an expression that involves the bitwise AND here, so 0 bitwise AND, and then whatever the result of full, when we run this, we would expect that full is called, and that's exactly what happened when we run it. Now, what if we use the logical AND? What if we do this? Well, let me start with false first. And so we would expect, in order to figure out the result of this whole expression, that full would be called, right? Now, when we run it, though, that's not the case. We don't see the in full message is printed. And the reason for that is the logical AND can be short-circuited. Then what that means is that because the first operand is false, we know that this expression cannot possibly be true. And therefore, it doesn't need to evaluate the second operand at all to know that. However, if the first operand is true, then whether the whole expression is true or not depends on the second operand, and therefore full will get called and evaluated in this case. All right, I hope that makes sense. And the next thing I'm going to talk about is the bitwise AND actually has a very, very useful property. So, and let's actually look at this truth table for the bitwise AND again. So, what happens when A it's 0, what exactly is A and B? And then the second question is, when A is 1, then what happens to the result of A and B? So as you can see from this table, when A is 0, it really doesn't matter what B is. The result is just all zeros. So the AND operation, together with one of the operands being a 0, is often used to turn off a bit. And then when A is 1, then A and B is just whatever the B operand happens to be. So the bitwise AND together with one of the operand being a 1 is often used to keep a bit around. So we can actually use these two properties together to create what's called a mask to examine only the bits that we are interested in. And let's see an example of that. So let's say we have a number, then this is the number, and we are interested in, let's see, the value at bit position 1. Okay, so the mask we are going to create is basically a number that has pretty much zeros everywhere except the bit position 1. And so we're going to set this to 1, and we will end the mask with whatever number is, and then we can see, okay, if it's anything that is not 0, which is going to be true, then it's on, and otherwise if it's a 0, then that bit would be off. So in this case, we would expect it to say that it's off, right? So there, it's off. Now, if we actually turn on this bit and we run the same thing again, then we can see that it's on. So this is actually very useful in a lot of cases that involves using bits to represent information. All right, so yeah, that's what this slide is. And next, I'm going to talk about a bitwise OR operation. Now, the bitwise OR for 1 bit, this is kind of the truth table for a bitwise OR, and as you would kind of expect, it looks like the logical OR operation. Everywhere it's 1, except in the case of if both operands are 0, then A or B is 0. And next, if the operands have multiple bits, then we do the same thing as before. We line up the bits, and then for each pair of the bits, we perform a OR operation. So 1 or 0 is 1, 0 or 1 is 1, 1 or 1 is 1, and 0 or 0 is 0. And that is, so this would be the result. As we just said, bitwise OR is actually very similar to the logical OR, which says is the result is true, except in the case of if both operands are false, then it's false. Now, I think you know what I'm going to say next, because these two are different in that the logical OR can also be short-circuited. So if we use the same example as before, then in this case, let's look at the logical OR, bitwise OR first. And if we run it, we see that full is called, and it really doesn't matter if this is a 0 or a 1. Full is always going to get called, right? Because again, bitwise OR or bitwise AND, they don't do any short circuiting. Now, however, if we do the logical OR, and in this case we do a true or whatever, it doesn't matter what the second operand is, this expression is always going to be true, right? So in this case, we would expect foo not to be called, and that is indeed the case. It just doesn't need to know what the second operand is to know that this expression is true. However, if we turn this to false, then the result of this expression would depend on the result of foo, and therefore foo is called. Next, we're going to talk about, well, the OR, bitwise OR also has very useful properties. So similarly to the bitwise AND, when A is 0, what is the result of A or B? And then when A is 1, what is the result of A or B? Well, so if you kind of follow the same pattern, then if A is 0, the result of A or B is basically what B is. So that's keeping B. Right? Now, if A is 1, then it really doesn't matter what the second operand B is. The result of A or B is always a 1. So then we can use this to turn on the bit. So this property, or the combination of this property, is often very useful to kind of selectively to turn on one or multiple bits while leaving the rest of the bits alone. Now, so after talking about bitwise AND and OR, then the last one we're going to talk about is the bitwise NOT operation. So NOT is basically a kind of invert a bit. So if the bit is 0, then not A or not 0 is basically just 1. And then if it's 1, then not 1 is 0. So, and the operator is this funny thing, the little tilde here. Okay, so that's for one bit, and then if it's multiple bits, then each of the bit is basically just flipped. So a 0, 1, 0 with each bit flipped basically becomes 1, 0 and 1, 0. Now, kind of the one very interesting thing that might not be obvious from here is that this original number, 0, 1, 0, it's kind of the same as, basically a lot of zeros to the left of this 0, and it would be exactly the same number, right? So what happens when you do a NOT on this number? What happened to all these invisible zeros? Well, all the invisible zeros actually becomes all the invisible ones, and that actually has some very interesting implications when we try to look at the result of a NOT operation, which I will show here. Again, I'll use the console here. Now, so if we, let's say, we have a very simple binary number 1, 0, and we're trying to invert it. And if we try to see the result, well, that is a -3. So what is -3 in binary? So let's actually look at it. In this case, -3 in binary, and it shows us we would expect that it's 0b and with flipped, so it will be 0b 01, but it shows us a -0b 11. That that might be confusing, and that's perfectly makes sense. That's just because the 0b10 is the same as 0b many infinite number of zeros and then 1, 0, right? Which if we invert it bit by bit, then it becomes 0b infinite numbers of ones and then 0, 1. which in what's this system called 2's complement, which is what most computer chips uses, it actually represents the number -3. Now, 2's complement is kind of beyond the scope of this class, so I'm not going to go into detail. But one thing I can assure you is that despite this looking kind of weird and not making a lot of sense, but I can assure you it is doing the right thing, and I'll do that by um, uh, doing this little demonstration, and that is, so if we actually invert this binary number here, 1 0, so it's going to become 1 1 1 1 1 1 1 0 1, and then if we end it with, let's say, a number that is all ones, then we would expect this to be turned off, right? And that is indeed the case here, and that is this bit actually gets turned off. So we're good despite this thing looking kind of strange. So having talked about all these bit operations, now it's time to try to practice doing some of these operations by hand. So please pause the video and try to evaluate these expressions and see what they become. And here are my answers, and so please verify them. Next problem. So let's say we have a number in a variable, and we can call this variable I. So what I would like you to try to do is to print out for each of the bits in I, if the bit is on or off. And we'll start from the least significant bit, bit 0, and go to bit 1, bit 2, so on and so forth, until we get to the most significant bit. And I would like you to, achieve this by doing a combination, using a combination of shifts and any of the bitwise and or not that you need to use. And obviously you would need a loop as well. So here is how I would do it. I'm just going to initialize I to some number, and what's important is the loop. So as long as I is not 0, I will just end I with just the least significant bit. So the first time it's going to end with this, and if it's on, then if it's non-zero, then it's on. Otherwise, it's gonna be off, right? Now, after I printed out this bit, I'll get rid of it by doing a left shift by 1 bit, and then I'll repeat the loop. So the next time it's going to be I and again 1, so it's going to give me this bit, and then it will do it again, and then I'll get rid of this bit again, and then so on and so forth. Okay, so let me run this, and indeed it give me well, the first one is off, right? It's 0, and then on, and then off, and then on. So this got it correct. Now this code does have a very subtle bug in a very special value of I, and I would like you to see if you can spot it. Feel free to discuss about that in the discussion forum. And this is the slide with the code, and oh yes, so if you think this is a little too long, then if you know how to use the ternary operator, then you can write it as one line. And one more problem, it's actually a fairly common problem. So let's say we have a variable called a val. It holds just 1 bit, so it could be either 0 or 1. And that 0 or 1 is at the least significant bit of val. And then we have another variable, I'm going to call it flags. This is actually used a lot in this kind of operation. That flag just, it's an int, and it can hold any value. And what we want to do is that we set one of the bits. So let's say bit 2 of flag to the value of val. Okay, and but that's the only bit that we want to change, bit 2 of flag. The rest of the bits of flag should be left the way that they are. So for example, if val is 1, then we want to set bit 2, which is this bit, to a 1. And then if val is 0, then again we want to set bit 2 of flags to be 0, and it's already a 0, so it's gonna be just 0. So I would like you to work out the rest of these other two cases, and then try to figure out a way to do this operation. So the most common way to do this, I'll show you now. The overall strategy is that we will first clear the bit 2 of flags, and then we'll take the bit in val, shift it to the right place, and then just put it there, put it in the position that has been cleared. So the way to first clear this bit is that we create a mask, and this mask is on is a 1 at this position that we're interested in, and 0 everywhere else. Now we're going to invert that mask, and we're going to end the inverted mask with flag. So basically the purpose is to clear out that bit 2 in flags. And after we clear that out, we are going to shift valve by 2 positions, so that whatever val is, whether it's 1 or 0, it's going to line up at bit 2, and we are going to OR it with the flags. And again, this position has already been cleared out, so when we do an OR, then whatever this val shifted by 2 is going to be set at this bit 2 of flags. And finally we can print it out. So I'm going to run this. So in this particular case, we have a 1, and we're going to set this to 1, so it becomes 1 1 0 1. And if this is 0, then we're going to set it to 0. Okay, and I'm going to leave you to test the other two cases where this is a 1.